Right, 12:05, time to start. Welcome everybody again. So last week we got the time going. We looked at what martingale is, okay, and we played around with examples and ways to construct martingales. So to recall, we have a filtered probability space. That means we fix a flow of sigma algebras, an increasing flow of sigma algebras, which represents our information flow. And then a martingale was a process which is integrable, adapted. So adapted means that each mn for a fixed n is fn integrable, so it's compatible with this information flow. And then it satisfies this property, which we rewrote in a number of ways. But somehow it tells me that my best prediction today, given everything that has happened up until today, of what's going to happen tomorrow, is the value today. Okay. And one nice way to construct more martingales was through this discrete stochastic integration. So if I had a martingale, I could take another process v, which was predictable, meaning vk is actually known one step in advance, so it's f k minus 1 measurable, and I can take this partial sums, and that gives me another martingale. And I could add an f 0 measurable and integrable random variable as a starting point. That doesn't cost me anything. We also said that we can always do this and hence move my martingales to start in 0 or not. Okay. So I want to use this construction to build an important example of martingales. So these are, let's call this stopped martingales and sampling theorems. There's nothing really difficult about this, but we'll call this first result a theorem because it's really very useful. Okay, so let X be a martingale. If I want to keep the notation from above, I will take this M. Let M be a martingale and tau a stopping time. This was then another notion that we've introduced. These were the random times, remember, such that they were compatible with our information flow. So when they happen, we know that they happen. Okay, so remember that tau as being a stopping time. This was the same as saying that tau equals to n belongs to fn for all n's. Right? So it's a random instant in time, but when it happens, I know that it happens. Then the stopped process, so m tau, so this is the process m at an instance tau minimum n, okay, is also a martingale. So when I say martingale, that means relative to the filtration fn, which is fixed there. But we also said that once you have a martingale which is relative to a filtration, then if you have a smaller filtration to which this process is adapted, it is automatically martingale with respect to that filtration. So it will be also martingale relative to the filtration fn min tau. We're using quite a lot of things here. This n min tau is again a random time, but we discussed that minimum of 2 stopping times is a stopping time. So this is a stopping time, and we saw how to define the filtration or the sigma algebra at that instant in time. So we know we can make sense of this information set at this time, which is of course random. So the second part of the result is clear. So I just need to show that it is a martingale, and I'm going to write this in the form above. Okay, so proof. It's very easy. So let Vk be the indicator that tau is greater or equal than k. So it's an indicator of a set. What is this set? Tau greater or equal than k. This is the same as tau strictly greater than k minus 1. And this is the same as tau less than k minus 1 complement. And so this is in fk minus 1. This of course, is union of tau equals to m from 0 to k minus 1. So this is in fk minus 1, so this is predictable. And so I know that this process x there is a martingale. What is this process? So xn, which is equal to, let me put x0 as m0 plus sum from n equals 1 to, k equals 1 to n, vk mk minus 1. But what is this sum? Well, vk is 1. Okay, it starts as 1 because tau is always greater or equal than 0. Well, if tau is 0, then I stop straight away. So then this is the first v1 is 0. But otherwise, v is 1 until k hits tau, and then from then onwards, it becomes 0. Right? So I'm just summing from k equal 1 to n min tau, where this is understood to be, let me put this like that. Okay, so if tau is 0, then this is really an empty sum. Great, but this means that this is nothing else because the telescoping sum, I get my final value. And so this result there tells me that this is a martingale. Well, I didn't discuss, so this is of course adapted. That's by, we know that this is, by definition, we've discussed this as f tau min n measurable. We had this result before, so in particular fn measurable. But the fact that this is fn measurable also follows from here. Okay? And likewise from here, I see that this is in L1, because each of these random variables is in L1. L1 is a vector space, so this is a finite sum of variables in L1. So this process is in L1. Okay? And when I had that it's a martingale, we also know that it's adapted. Of course, each of these is fk measurable, so the whole thing is fn measurable. And the fact that this is f tau min n measurable allows me to conclude this last bit there. Great. So I know this is a martingale. That is my first key result. Okay. But I can actually say a little bit more, right? So this in particular tells you that conditional expectation of m tau min n given f tau min k, let's say, is equal to m tau min k, where k is less or equal than n. And now I want to do more. I would like to just have two arbitrary stopping times where this is larger than that, of course. Okay. So this gives me this martingale property along a particular sequence of stopping times, which are constructed from one stopping time and then taking minimum with integers. And I'm going to extend this to more general stopping times. So this will be, again, a theorem. This is now Doob. you will see this under different names. Call it here Doob's optional sampling theorem. A subset of this result is often referred to as Doob's stopping theorem. And as far as I'm concerned, you can use the two interchangeably. Okay. So let M be a martingale. Of course, on our fixed filtered probability space as before. And tau, which is less or equal than rho, 2 stopping times. Then expectation of m rho given f tau is equal to m tau almost surely. So I don't have this, unfortunately, at this moment for any 2 stopping times. I need to assume something more about them, so not ordered order, but and I want this to be in different color. I need to assume those stopping times are bounded. Okay. Of course, you can take expectation on both sides of this conditional expectation, and you get that in particular expectation of m rho is equal to expectation of m tau is equal to expectation of m0. And this part is often known as the sort of stopping theorem. So what do I get? I get in particular that if m is a martingale, then expectation of m at any stopping time, any bounded stopping time, is constant and equal to expectation of m0. And as an exercise, on the problem sheets, or mark maybe exercise, you can show the converse. So a converse would be that an integrable adapted process m such that this holds for any stopping time is a martingale. Okay. So even though this seems much stronger, if you get that for all bounded stopping times, then you can show that m is a martingale, and then hence in particular this holds. Okay, let's prove this. So first case, assume that rho is just an integer. Okay, so if rho is an integer, in particular, rho is bounded by the same integer as it's equal to, and tau by assumption is less than rho, so tau is also bounded. So I want to show this with rho equal to n. Okay, and I'm going to take set A in f tau and check the defining relation. I already know that m tau is f tau adapted, so I just have to check that the defining relation for the conditional expectation holds. So I need to compute expectation of mn indicator A. Yeah, and I would like to show that this is equal to expectation of m tau on A. Now this is the same as expectation of mn indicator of A, indicator tau is equal to k, k from 0 to n. I know that tau is less or equal than n. Now what do I know about this? By definition of f tau, a set of this form, so intersection of A with tau equals to k, belongs to fk. But if this belongs to fk, then this, by the defining relation property of conditional expectation for Mn is equal to, so I'm using here, what am I using? I'm using here that the conditional expectation of Mn given Fk is equal to Mk. And that's just the martingale property of the process M. But that means that if I hit Mn with a set in Fk, then it's the same as hitting Mk with this set. So this is Mk, indicator of A, indicator tau is equal to K. But of course, K on the set tau equals to K, I can replace that with tau. And then I can sum up, now this doesn't depend on K, and so I get this is equal to expectation of M tau, indicator of A. So that establishes the result for the case for rho, the largest stopping time is a constant. So now for the general case. I'm going to use this result there, okay, with tau n with rho. So I'm going to let yn be the difference between the stopped martingales. So this is a martingale, and that is a martingale. Difference of two martingales is a martingale. So I know that y is a martingale. You see sort of it's a particular martingale which I try to pick up the bit of M which happens between tau and rho. So this is a martingale. Okay, so what do I know? I'm going to look at y tau min n. Now, y being a martingale, I can apply case 1 to y. Okay, so apply with rho equals to n. So by case 1, I know that this is equal to expectation of tau n, sorry, rho yn given f tau min n. But this is, by definition, expectation of m rho min n minus m tau min n f tau min n. Linearity of conditional expectation tells me that this is difference of conditional expectations, and so I get this is equal to expectation of m rho minimum with n f tau min n minus m tau min n, almost surely. But what is this random variable? Well, if I plug tau min n here, then I get m tau min n, so tau minimum n, that's just 0. Okay. So in fact, I have that this is equal to this, and now rho is bounded, so take n large so that rho minimum with n is in fact equal to rho. That's the moment where I'm now using the fact that rho is bounded. And then you get that expectation, conditional expectation of m rho given f tau min n tau min n, of course, is also equal to tau, because once this happens, rho is larger than tau, so tau minimum n is equal to tau. And I get the equality that I wanted to have here. This just follows by taking expectations. So that finishes the proof. And as a cautionary remark, we should straight away observe that this assumption of bounded is important, right? So if you consider M a simple symmetric random walk, and tau, which is the first hitting time of 1, so this is the first time that my random walk is equal to 1, that stopping time is quite easy to show. This is something we'll discuss later on more, but you can do this yourself, that this is finite almost surely, so I do get to 1 in finite time. It's not bounded. I could start by going down and get quite low, but at some point I'll go up again. Okay, so this is bounded. Sorry, this is finite almost surely, but not bounded. Okay? In fact, you would have already seen this with Markov chains in part A probability, that the hitting times like that are well defined. So this being finite almost surely tells me that m tau is equal to 1. Okay, and so clearly expectation of m tau is not equal to 0. So that simple consequence doesn't hold. Okay, so our next aim is to remove that bounded. Okay. As this example shows, I have to be careful, but also as this example motivates, I do, a lot of my natural stopping times are not bounded. We already talked about this. Hitting times are quite sort of naturally the way we were going to define stopping times, and they're not bounded. Okay. So if you have a statement in maths, okay, and you'd like to remove one assumption, and you have a counterexample, well, clearly you'll have to add another assumption. Okay. So something will have to give, and I didn't have many assumptions. I just assumed M was a martingale and tau and rho were two bounded stopping times. Okay. So if I want to extend this to unbounded stopping times, clearly I'll have to assume something more about my martingale. Okay. And now the quest is to try to get a sharp result and really assume as little as we need on our martingale. Okay. And then brings us back to the notion of uniform integrability, which I sidelined for, in our discussion of integration before, because we didn't need that. So now we go back and we do a bit of technical work to introduce this notion of uniform integrability, so that we can then get back here, and we'll see, hopefully, at the end of tomorrow, that if I add uniform integrable here, I can remove the bounded. Okay. So that's our aim. I'm going to put this maybe in red. Okay, I can remove that, but I need uniform integrable. And that doesn't make sense yet because we haven't introduced this. Okay, so we're going back to chapter 5. But before we do this, on our way was chapter 6, where I've also skipped one tiny detail. So somebody pointed this out. So a bit of household keeping. We're looking at this. We had this result about existence of L2 projections, and we had L2 space x a variable in L2, and k a complete vector subspace, and then we actually shown that this infimum, so projection in L2 sense onto k of my variable z, of my variable x, is attained. Okay. So we've stopped here. That's what I've shown you, and I said that this y has the property that it's orthogonal. The remainder x minus y is orthogonal to the k, but I did actually write down a proof of that. The proof of that, so this is the one thing that remains to be shown, this one. And I didn't do this because it's the same if you do this in Hilbert spaces, in this L2 space, or in RD. Okay, but maybe let's do this just for completeness. So existence was done, and now orthogonality. Okay, so take z in K, and we need to show this. Of course, if z is equal to 0, then there's nothing to show. So I'm going to assume that z has a positive second norm. And I'm going to consider x minus y plus tz. So what do I know about this? I know that K was a vector space. So y is in K, z is in K, t is some number. So this is still in K. Now, if this is in K, then optimality of y tells me that this has to be larger than x minus y. Okay, so this difference is not negative. Now, of course, you can think of that as x minus y minus tz, and you're going to square it. So if you expand both of these expectations and squares, this bit will cancel out. And what is it that you have left? It's t squared, the second norm of z, and then minus 2t, and then expectation of what you wanted. So this times that. Now, this is for all t's in R. So now I'm going to take a specific t. So what t am I going to do? I'm going to try to minimize this, right? That's what you would do. So I'm going to take a t which minimizes this, which means I have to get these two to be proportional to each other. So I need to take t which will cancel that. So I'm going to take t which is expectation of z x minus y divided by second norm of z. Okay. So then when I square t here, this will be z power 4. We'll cancel out with that. And I'll just have this. So in total, I get minus expectation of z x minus y squared, and then divided by z squared. But those are both squares. So this with a negative sign. So this is less than 0. And so, in fact, it has to be 0. Okay? And what does it mean that this is equal to 0? Well, this, of course, means that t is equal to 0. And that means that this is equal to 0. Okay. I think you'd essentially probably have done the same in RD when you're doing projections in earlier years. Okay, so that's, I think, the only bit that was outstanding from chapter 6 to show. So now I'm back to uniform integrability. Definition. So the collection of random variables, let's call it C. And so random variables are just functions on omega, right? At this point, I don't have a filtration. We have a slightly poorer setup. We don't need filtration because we don't have any time. We're just thinking about collections of random variables. So this collection is said to be uniformly integrable. Which I'll always just denote as UI. If the following happens. So I'm going to look at expectation of x on this set where x is large. And I'm going to take a sup over all x's in my collection and limit as k goes to infinity. And I want this to be 0. So remark or example, if I take a collection of x which is just composed of one x, which is in L1, then a single random variable which is integrable is also uniformly integrable. This is just dominating convergence theorem, right? DCT, because you can, well, I guess you can take yn equals to x indicator x greater than n. Okay, this of course goes to 0 almost surely, and each yn is less or equal than x, which is in L1. So we know that expectations of yn converge to 0. Okay. And okay, here I have sequence, but this is of course monotone in K, so I don't have any trouble in sandwiching things in between. So one integrable random variable is uniformly integrable, and clearly, if you look at this definition, if you have two collections which are both uniformly integrable, then their union is also uniformly integrable. So, in particular, a finite collection of integrable random variables is also uniformly integrable. So if C1 and C2 are UI, then C1 union. The other remark which is useful to make is that this choice of function here is somewhat arbitrary. You can replace that function with any other function that somehow tests how quickly your tails disappear in integration. What is really, really key is that I have soup over the whole family here. So what we've just said is that this always goes to 0 for a single random variable, which is integrable. But this soup here is what really is important. So one such example, maybe of a function which will be useful. So if I look at x indicator x greater than k, this will be greater or equal than x minus k positive part. Okay, because this function is, well, it's equal to x greater than k minus k on this set, so it's clearly less than this. And on the other hand, I can put this maybe to be less than twice x minus k over 2 plus, right? If x is greater than k, this is a non-negative function, and on this set, this is at least k, so this is at least k over 2 times 2, so you'll get the right formula. So that sort of compares you that if you can sandwich this function between other function of the same type, of course, I take limit, then if I can show that the limit there above with these functions works, then it works also with the one in the middle. Okay. So theorem. Let's try to make it into more, sort of characterize this. So a collection of random variables, a collection C of random variables is uniformly integrable if and only if the following happens. The first condition would be that supremum over x in C, expectation of x, is finite. And the second one would be that for any epsilon, there exists a delta such that sup over all a's in F with probability of A less than delta, expectation And then I also want to have sup over x's. X indicator of A is less than epsilon. So if you're UI, you're bounded in L1. But not only this, but also this happens. So what does this say? It says that if you want, you can forget about epsilon and just say that this goes to 0 as delta goes to 0, right? It tells me that I can look at all small sets, and then I can look at expectation of my x on a small set, and then this will be controlled. We'll prove this in a moment, but let me first state a result which somehow motivates what's going on, and maybe gives you an insight of why this notion is important. Okay. Maybe I'll state it here. So this is theorem 524 in the notes, and this is known as Vitali convergence theorem. And you can sort of think of it as a finer version of dominating convergence theorem. Why that really makes things work. So let Xn be a sequence in L1 converging to X in probability. Then the following are equivalent. One, this collection is uniformly integrable. Two, the limit is in L1 and Xn converges to X in L1. And then 3, the limit is in L1 and expectation of Xn converges to expectation of X. So why do I say that it generalizes dominating convergence theorem? Because dominating convergence theorem would tell you that if your Xn converges to X, well, almost surely, so from probability I can extract a subsequence and get it converging almost surely, then if Xn's are dominated by an integrable random variable, then they converge in L1. From this example, okay, you can clearly also see that if C is such that X is less or equal than some Y for all X's in C, so if my collection, however large, is such that each element here is dominated by a single random variable, okay, then this also means that X indicator X greater than K is less or equal than Y indicator Y greater than K. Okay, X is less than Y, and this is a larger set. And I know that this quantity converges to 0 as K goes to infinity. Okay, so I see that C is uniformly integrable. So a collection dominated by an L1 random variable is uniformly integrable. So in DCT, you would have Xn's dominated by Y. That implies that they're UI, and that implies that they converge in L1. Okay. So this is finer. I get it for convergence in probability. And I have now equivalence. Okay. In dominating convergence theorem, I did not have equivalence. I cannot go back, because that's actually the precise result. So for those of you who might be doing further functional analysis, and at some point, if in your functional analytic journey, you can sort of skip this first assumption, and you can just try to think, where is it true that from a sequence in L1 you can extract a converging subsequence? Okay, so that would be essentially compactness in L1. Okay, so in R or RD, well, compact set is a set which is closed and bounded. So forget about closed because I'm just interested in relative compactness, but you need bounded. Okay. In L1 that's not true, and it turns out that uniform integrability is in fact the same as relative weak compactness. So then of course you have to understand in which sense you want to converge, and we had this notion of weak convergence in L1, which will be the appropriate one. But being bounded, which is here, okay, that tells you that you're within some ball of fixed radius. That's not enough. Okay, that's not enough to get you compactness in L1, or weakly in L1. Okay, so we have 10 minutes. Let's start proving things. We'll probably not get through the proof of this and that, so we'll start with this. Should be able to do this, and we'll get back to Vitali tomorrow and finish the proof. Okay, but together those two results will really tell us that this is a useful notion, the one that really characterizes when I can go from convergence in probability, so relatively weak notion, to convergence in L1 and back. Okay. That's the interest. The definition itself, of course, is somewhat dry. So this result, which I call theorem here, in the notes it's called the proposition. It has number 522. So let's prove this first. Let's go this way. So assume C is UI, and let's prove 1 and 2. So let epsilon be greater than 0. And let's look at expectation of x, indicator x greater than k. Okay. I know this goes to 0 because x on its own . So I've assumed this is uniform integrable, so I have that this limit is equal to 0. So this quantity goes to 0 uniformly. Okay, and so I can put this less than epsilon, or maybe half of epsilon. And this will be true for any k greater than some k epsilon, which I can fix. Okay. Well, in particular, if I look at expectation of x, this is equal to expectation of x, indicator x less than k plus greater than k, and so this is less or equal than k plus epsilon over 2. So it's uniformly bounded across my family. So that tells me that 1 here is satisfied. Okay. But I'm more interested in 2 now. So I'm going to put delta small, so delta will be epsilon divided by 2k. And I'm looking at this property here. So I take A, which is small. And I put expectation of x, indicator of A. This is expectation of x, indicator of A, indicator x greater than k, plus expectation of x, indicator of A, indicator x less or equal than k. This bit here, I'm just going to replace x by k. So this is k times probability of A. Probability of A is less than epsilon over 2k. So this will be less than epsilon over 2. And here I'm going to forget a, because I already know that this is small. Okay. And I get my inequality. Essentially, all I did here is both of these are very small sets, right? So I can just focus on one of these two sets in each case. Right, so now we need the converse. So I'm assuming 1 and 2, and I need to show that my family is uniformly integrable. So I fix epsilon. I know there's a delta for which this holds. And I also know that this supremum is finite. So I'm going to call this bound on the common bound on L1 norm of my random variables M. So now probability that x is greater than k. This is of course less or equal by Markov inequality expectation of x divided by k. So this is less than m divided by k. And so if I take k large enough, let's say take k which is greater, so I want this to be small, so I want this to be less than delta. So for this to be less than delta, I need k to be greater than m over delta. Okay. So I took large k, I compute this, and I realize that the probability of this set is small. Small enough so that I can use this property which I know holds. Okay, and then the second property straight away gives me that this quantity is uniformly bounded across all x's in my class C. Great. Any questions? It's all clear? Okay, so we won't prove Vitali, but let me just state and prove a very simple lemma that will be useful tomorrow on our way to proving Vitali. So let psi n converge to psi in probability. A sequence of bounded random variables. Okay, so my psi n's are all bounded. So by this I mean that psi n is less or equal than k for all n's, okay, and also psi. Then psi n converges to psi in L1. So I take epsilon positive, and I look at the set where psi n minus psi is greater than epsilon or greater or equal than epsilon. I know that probability of an goes to 0 because that what it means that psi n converges to psi in probability. Okay. So now I'm going to look at expectation of xn minus x. I'm going to split this into 2 bits. One will be on an and one will be on the complement. So this expectation of xn minus x indicator an plus expectation of xn minus x indicator an complement. On an complement, this is small, okay? let me take epsilon over 2 here. This is small, in fact, it's less than epsilon 2. So this is just less or equal than epsilon over 2. What about this? Sorry, I'm writing x and I really mean psi everywhere. Good. What's happening here? Well, this is less or equal than 2k. So this is less or equal than 2k probability of an plus epsilon over 2. But probability of an goes to 0. So n large enough, I can make this as small as I wish to. Okay. So this is less than epsilon, taking n large enough. Specifically large enough, so the probability of this is less or equal than epsilon divided by 4k. So that, of course, gives me that this goes to 0, and that's the end of the proof. This trick that we did here, look, we did it also here. Okay. It's quite a useful thing, and we do this time and again when you have expectation and you have some partial information about this object you're integrating. You split your integration into 2 bits and then reason on the sets, and usually things then follow through. Okay, I think we'll stop here, and then tomorrow we'll start with proving Vitali's convergence theorem, and once we have this, we have all the ingredients to then go back to our martingales, add in the uniform integrability assumption, and try to get the Doob's optional sampling theorem for any stopping times, but without this. And if you want to think about something for tomorrow, here's another simple result that we'll start by proving tomorrow, which is that if you have family of sigma algebras F alpha, let's say, they're all sigma algebras, and you have X, which is in L1, then expectation of X given F alpha, this family of random variables is uniformly integrable. Okay, so if I produce random variables through conditional expectations of one single integrable random variable, whatever cardinality of F alpha here of this family, this is always uniformly integrable. That was one example that we did this in this way to produce martingales, and this you'll see will tie the whole story, and we'll see that martingales produced in this way are uniformly integrable, and hence we'll be able to use Doob on them with arbitrary stopping times. I'll see you tomorrow. Thank you.